suppose, is always natural temporal, so new elements appeared at some point. So all data in Beam has a timestamp, and this is a timestamp when the data logically was created, for example, when the user clicked on the link, as opposed to when this pipeline saw this part of the button that the user clicked the link. It is really important because it lets you define sensible semantics, independent on the execution details. Let's see how this programming model applies to these two primitives. For Pardo, it's pretty trivial. When new data arrives, you just apply the function to it, and you're done. As for aggregation, it's a little more challenging, because normally you would say that you group all elements with this key, and you say here's group. But in this setting, there is never such a thing as seeing all elements for a particular key, so we need to define it in a more general way. Let's talk about that, because this is really the only thing that presents a problem for people learning Beam. How Beam does that. The idea is that Beam buffers data per key, so the group by key operation takes a collection of key value pairs and emits a collection of pairs of key and multiple values. If you mentally partition this by key, you can think of it as a collection of buffers, where for each key, values arrive, and sometimes we emit groups of values to the output when we think that we've seen enough. We will never see all of them, but we might at certain moments decide that we've seen enough to emit some intermediate aggregation result. So think of it this way. This arrow is the axis of event time. This is not the whole clock time that passes. This is the logical axis of when things happen. And new events arrive in, or sort of rain onto this axis and arrive at different times and arrive onto different points on this time axis. And occasionally, results come out. A more complete formalism for this is called strings and tables, and I highly recommend this presentation, I think, by Tyler about modeling Beam in the strings and tables theory. But at a high level, we have a stream of inputs and a stream of outputs and some controlled way to decide when to emit the outputs. So let's look at this in still more detail. So this is slightly convoluted, but this is the exact mechanics of what happens with aggregation in Beam. When the data point arrives for a certain key with a certain value and a certain timestamp, we apply the idea that when you're dealing with temporal data and when you're aggregating it, you also almost always want to aggregate it into time buckets. You rarely need the aggregation over, like, since the beginning of time. If you want that, that is possible too. There is the so-called global window. But generally, you want every element to contribute to aggregations in multiple windows. For example, you might use fixed windows or overlapping sliding windows, or you might use session windows, and so on. The key point is that every element contributes to one or more windows, and each of the windows internally has a buffer of elements that have been contributed to it, elements that sort of belong into this window. And inside each window, there is a little machine called the trigger that decides what to do with the new elements. When a new element arrives, we perform one of three actions. Either we drop the element. If the element is way behind, for example, we receive data that maps to a window that was closed a year ago, and we decide that this is the kind of data we just want to ignore. So in some cases we may just drop the data, that is called slate data. We can add it to the buffer and do nothing else yet, or we can decide that we have accumulated enough data for this key window and say, okay, here's the next group for this key window, and the pipeline will do something with the group. That is pretty much it, except there is one more detail, that's so-called watermark. Watermark is a continuously increasing estimate of how old data do we think we're going to see. It has to be provided by the data source, because in general there's no way to estimate what data is going to come, but some data sources are able to provide this sort of estimate, and Beam can make use of this estimate. For example, if the watermark says that it's quite likely that no data is going to arrive before an hour ago, then we can emit the results in all windows older than that. So together we have these mechanics going on, and as new data arrives, it either gets buffered or discarded, or aggregation results get computed and emitted. This is the core of the Beam model. It is the subject of a lot of misunderstanding, but I'm hoping that this explanation will clarify it. Okay, so the key idea is that the key idea behind Beam's unified model is that there is no distinction between batch and streaming. These terms do not even exist in Beam's programming model. There is no such thing as a batch dataset or a streaming dataset. They're just a collection. The thing that we perceive as the distinction between batch and streaming is different ways to control aggregation of data and different ways to decide when we think that we've seen enough. Okay, the next core pillar of Beam is its portability, and here I'm going to present Beam's vision. It is not 100% of that yet. The work is on track to be completed by the end of 2018, but I'd like to give a sense of where we're going. We're going to a world where you can program pipelines in any language that has a Beam SDK. Currently that is Java, Python, and Go, and new languages can be added in the future. There is also a Scala SDK created by Spotify. All that gets translated to a portable website representation, and that representation can be run by any Beam runner, of which there are currently, I think, 9. Some examples are the Spark runner, Flink runner, Google Cloud Dataflow, Local runner. So the thing is that you can program in any of these languages or a mix and run it on any runner. This has a number of obvious and less obvious advantages. First, there's the obvious advantage that you're not locked into using any particular runner. For example, suppose you have a Flink cluster, and later you run some Beam pipelines on it, and then you decide that actually I don't really like how my Flink cluster is handling that. I'm going to check out Spark. And maybe you like Spark, maybe you check out Dataflow, like it even more, all that without modifying your pipeline. The other benefit is that there is no language lock-in, and by that I mean that you don't have to commit to a particular language before ordering your pipeline, because you can use transforms written in any language from any other language. For example, you can be primarily a Python programmer, and are we completely out of time? Almost. Okay, so there is no language lock-in, and there is no language lock-in for library authors either. And also this gives sort of linear rather than quadratic speed of growth for combinations of runner and language. For example, I think the capability to run Go on Flink is free once you have a Flink runner and a Go SDK. So I think that is really important. This is just a map of the Beam ecosystem from the lowest levels to the highest. There is a number of runners, there is the model, there is various languages and families of libraries and various ways to program Beam, like SQL, third-party SDKs, and on top of that there is user code, or there are products, like whole products and businesses and services built on top of Beam. Tyler is going to talk about one of them, and there's a number of others for data preparation. And on top of that there is, of course, the Beam community, which I found to be incredibly friendly and welcoming, so I encourage you to join it. That is pretty much it. So with that, I invite you to listen to Tyler's talk that comes after mine, and he will talk about Beam applied to machine learning. Thank you.
We're going to talk about Gimel, and what I'm going to do in this short talk is set up the reasons why we built Gimel. So we're going to talk about the challenges that we saw at PayPal, and we do believe that those challenges are not just PayPal specific. Any enterprise that has just moved to the big data world or is fairly new to the big data world will face all of these challenges. So quick introduction. So I'm a product manager for data processing products at PayPal, and I also have with me Deepak sitting right here, who's the engineer on the big data team. So why Gimel? So assume you are working at a company or a business unit within a company who's charged with creating something like this. It's a flight cancellation dashboard. Build a dashboard that shows how many flights were cancelled by month, what are the top 10 days that which had the most flight cancellations, the airports impacted, the airlines, and what was the reason. And then maybe throw in a visual on a map to show where are the most cancellations happening. You are an analyst. There are several challenges you will face when you're given this kind of a task. First of all, you have to figure out what your data points are. So okay, looking at the dashboard, you can figure out you have some flight events, you have airports, you have airlines, you have carriers, geography, and then some sort of geotag to link a latitude and a longitude to a city. So in a company like PayPal or any other big company, first challenge is where is all the data? So you know that this data exists somewhere. You have probably multiple catalogs. You have a lot of tribal knowledge. You ask around your team. You ask other units. You look up some wikis. You look up actual catalogs. Okay, you figure out that the data exists in across Kafka, across your data warehouse. In this case, let's say Teradata, and then you have to get the geotag kind of information from some API or for some text file downloaded from some website which has a mapping of latitudes to cities, and you're going to process it in your big data world in Hadoop. Okay, you got all of that. Now, as an analyst, you have to figure out how am I going to ingest this streaming data from Kafka. I have the data in Teradata, but I need to bring it to Hadoop. What kind of process am I going to run? And then how do I load this external data into Hadoop? Once you figure all of that out, you also have to actually process it. You have to link it. You have to cleanse the data. You have to link the data so that it's presentable. It's in a format that can power the dashboard. When it comes to processing, you also have to then figure out, am I going to write it as a Parquet file, as an ORC file, as a plain text? What is going to be my output format? After having done all of that, so that's just whiteboard, right? Okay, how am I actually going to run it? So typically in the big data world, because there's a lack of good interactive SQL or querying type of tools, you have to log into some sort of a CLI. You have to go to some gateway host or a bastion host, and then go to your cluster, start writing your queries. And once you write those queries, you also have to figure out how am I going to publish this. Is it Tableau? Is it, in this case, we have given an example of Kibana, but how am I going to publish this data? And once you do all of that, let's say you figure out all of these things, you have a good POC created. What's the next step? You want to run this on a schedule. So how do you productionize it? Typically, we have seen in the few companies in the PayPal type of size, there's usually an analyst team and there's an engineering team. The analyst takes all the POC code and hands it over to an engineering team that has the task of translating that into production-ready code. And that team then has to figure out how to do the logging, monitoring, alerting, auditing, making sure the data quality is good, because then that is what defines the production quality code. All of these challenges are just from a simple use case perspective. If we double click into some of the specifics, let's say your chosen Spark. This is not related to POC, but just in general in the big data world. Let's say your choice of compute engine is chosen Spark. That's just one example of how to read from HBase using Spark. Don't go into too much of the detail of the code itself, but there's a lot of physical properties of where is my HBase cluster, how do I connect to it, and all that included in that code. So it's a very cumbersome code that you have to maintain, and as we'll see, it's very fragile as well, because anytime something changes in that, you have to touch this piece of code. Now, just multiply that by how many ever data stores you have. It's very rare in the big data world to have, unlike in the RDBMS world where you chose Oracle and everything that you do is in Oracle. Here you have very specific use cases addressed by very specific data stores. So Elasticsearch, Aerospy, and so on and so forth. If you have a mix of these, you can imagine that as part of maintaining your business logic, you also have to maintain all this cumbersome code. In addition to that, because there is no central catalog, you have a whole bunch of data set related challenges. We already looked at how it's hard to find data sets. We already looked at the fact that the code to access these data sets are tied to the compute and the storage. But then also, when your analysts are familiar with SQL, even if your data is getting generated in Hadoop, you have an additional task at the end of the process to move that data to your SQL store, let's say Teradata. That creates duplicity. That you have data that is in Hadoop that is physically brought over to Teradata. It has latency, but also it has duplication of data. There's no standards. How do I know as a team, let's say that the POC, the flights cancel team, I'm producing this data, how does the rest of the organization know that there is this beautiful data set available? There is no standard process for that. There's no audit trail. So let's say in fintech, for example, there's a lot of scrutiny on what kind of data has been accessed by whom. There's no audit trail because the data is across the board and no one knows who's accessing what data. And on the same line, because we don't know, we cannot run any kind of trends, and as a result, it's very hard to figure out what data can go to a cold store, what can stay in the hot, and so on and so forth. All of this leads to a life cycle that looks something like this. The first time you decide, okay, I want to build a big data application, you go through the process of learning and you code and you optimize and you deploy. Let's say that was 3 years ago and you chose MapReduce. Now Spark is the rage, so as soon as you choose Spark, you go to the entire process, potentially touching every part of your code. Let's say you went from Spark 1.6 to 2.2, guess what? You have to do all of that again. Let's say your storage API change, so you went from 0.5 version to 0.10, all of that has to repeat. If you upgrade a connector, the connector itself has its own evolution maintained by someone else, and you want to get those bug fixes or new features, performance optimizations, guess what? All of that. Your IT decides to move to cloud, so they're going to move your host from on-prem to cloud, guess what? All of that has to repeat, and so on and so forth. So you can see that because of the way the code is and because of the way the ecosystem is, anytime any of these minor things change, all your developers have to go through this process, and that's not very beneficial to anyone. Infrastructure team cannot innovate, cannot bring new features, performance enhancements, bugs, results, and development teams are lagging behind on innovation. And that is why we built the Gimel data platform. What does it look like, the entire ecosystem? It looks something like this. And we're going to, Deepak, in the long talk following right this one, is going to talk about this piece, which is the core of the data platform. It is powered by a central catalog and API, which also provides SQL access to all of the data stores. But then it'll be unfair to say Gimel data platform lives by itself. It is very closely integrated with our compute platform as well. We won't talk about it here, but we are here all day, so we can talk about it offline. And then it is the user experience will be through these two. So if you're a developer, you have an SDK, and if you're an analyst or just want to use SQL, you will have notebooks, Jupyter notebooks that are tightly integrated with the platform that you can run your queries on. So those are the three pieces of Gimel data platform, and we'll focus on the data API as well as the catalog. What happens at the end? So you have all of those challenges through these two sets, the notebooks, I'm talking about notebooks, think of it as Jupyter, through Jupyter notebooks and the data API catalog and the tools around those, you should be able to go, and then in the following talk, Deepak is actually going to show he'll be providing the demo to show how it is possible. I'm being told my time is up, but just to leave you with a summary, what is the Gimel data platform? It's a simplified and unified data access. It is a single API. It has a SQL layer, which is very powerful across all stores, whether they provide SQL or not. It's integrated with Jupyter, so your analysis and your prototyping can all be done through notebooks, and underneath it's powered by the Gimel compute platform. We have code labs at 10:55, but if you want to get ahead of that code lab, just go to try.gimel.io. There's a bunch of prep work that you can do before the code labs, and then you can come to the code labs and we can answer questions for you. Sounds good?
I'm going to be talking today about applying deep learning to sequential data. So, over the past few years, there's been this explosion of advancements in deep learning. You hear a lot in the news, there's always advances in research, but as a software engineer, it can be kind of hard to know what actually works in practice, like which advances you kind of need to pay attention to, like which things are most applicable to what you're working on. So my goal for today is just to kind of share with you some of the techniques that have been useful in my own work. And it's a short talk, so I'm really just going to have time to give sort of the high-level intuition for like how and why things work. And then if you find that these are relevant to your work, we'll have some pointers at the end for where you can get started with actually implementing them. And if they're not relevant to your work, then at least you'll be familiar with the terms, so later on when you hear them, you'll know what people are talking about. So the software kind of sequential data we've been hearing about today, I'm going to specifically focus on language, human language, not programming language, natural language, or written language, text. Text at the end of the day is just a sequence of words. So when we're trying to understand sequential models, I find that text is a really nice medium to kind of use for example. So for example, here's an email, we can just take an email and break it into words, and now it's a sequence. Text also happens to be my area of expertise. So just a little bit about me. I'm from a group called the Google Brain Team. We kind of do a mixture of research, software, and applications, all centering around machine learning. I personally work at the boundary of research and applications, what you might call applied research, specifically focusing on anything with language understanding. So one project I recently worked on that I really enjoyed was launching SmartReply. SmartReply is where if you're looking at Gmail on your phone, you'll see some suggestions that are automatically created for responses. For that, we used a deep learning model, and I thought it was a lot of fun. So some of my examples will kind of use that, but the general ideas I'm talking about should apply to other types of data too, not just text. Okay, so the main tool that I want to talk about today is recurrent neural networks, and how they're very powerful for modeling sequences of data, and maybe you've already been hearing about them today. Before we can get into recurrent neural networks, we have to start with plain old feed-forward neural networks. So how many of you have seen neural networks before? By show of hands. Oh, okay, great. How many of you have actually implemented one, maybe deployed one or something? Okay, great. And we can go really quickly through this. I just want to make sure we're all on the same page, so I want to really quickly cover the basic feed-forward neural network. I'll quickly do it since most of you have already seen it. Basically, if you've seen neural net before, you've probably seen this very classic example. This is handwritten digit recognition. The input is an image of a digit that was written by humans. The output is a computation of what digit that is. The basic building block here is the neuron. The job of the neuron is just to learn one little function of the data. It gets the input, which in this case is the pixel value from the image. It learns some weights, and then computes the difference of the weights and the inputs past through nonlinearity. You put a bunch of these neurons together, you get a layer. You put a bunch of layers together, and you have a deep neural network. How do we learn the weights? Through the process of gradient descent. So that means is you get a bunch of examples of data. So in this case, that would be a bunch of images and their labels. And then for each one you pass through the neural network, you look at the correct output, what it should have been, the ground truth, what the neural network said it was, you compute a loss, and then you use that to update all the weights just a little bit in the right direction. Do this over the course of all your training examples, and for a problem like this, you can actually learn a very good model, although this may sound like a very simplistic way of optimizing it. But the key takeaway, the key thing here is just that the neural network is learning everything from the data. So of course, there's no programmer sitting there saying like this is what a 1 looks like, it's like a bunch of pixels in a row like that, or like this is what a 2 looks like. There's not even someone saying what the different features are. So in traditional machine learning, there's a lot of feature engineering. Neural networks relieve a lot of that. Another way to think of that is that this hidden layer in the middle is an internal representation of the input. The neural network is learning its own feature representation, how, like what it thinks are the most important features to make its predictions. Okay, so that's kind of quick 2-minute primer on feed-forward neural networks. Now let's talk about recurrent neural networks. So in the example I just showed, and in kind of the most popular applications of neural networks, there's one input, one output, an image, and then a classification. Recurrent neural networks handle sequences. So what this means is that instead of just seeing each input especially, they can see a whole sequence of inputs and not forget the input they saw before. Okay, so for example, if our sequence was an email, right? I said an email is just a sequence of words. We can see that into a recurrent neural network one token at a time. So first it sees the word, let's say the email is how are you? First it sees the word how, and it reads that into its hidden state. Now its hidden state is its internal representation of the word how. Then when it sees the word are, it's not going to forget how. See that box, that blue box, which I'm using to kind of represent the hidden state, has arrows from both the previous hidden state and the word are. So that means that the new hidden state is a function not just of the current input, but also of the previous hidden state. And so on, it reads each token in, and by the end, after it's seen this whole email, the very short email, how are you? We think of this hidden state of the model as this internal fixed length encoding of the message. So why am I saying fixed length encoding? Because the sequence could be any number of tokens long. It could be a 200-word email. But I, as a programmer, am going to set the size of that hidden state to something like maybe 512. And so it means no matter how long that email was, it's going to encode it in 512 floating point numbers. Now, that might sound strange to you. You're thinking, how can you take any arbitrary email and put it into this, just 500 floating point numbers? This is kind of part part of the magic of neural networks is that through this process, it's really forced to extract the most important information. This is kind of like a bottleneck. It's kind of like a bottleneck to take like this very large, sparse, highly variable input and compactly represent it in its own way. And depending on the objective, it's forced to do that in a very efficient way. So our hope would be that different emails that are very similar, like how are you doing, what's up, they're all going to have very similar encoding just because of exactly the sort of bottleneck that's pushing things together. Okay, so now that would be useful if we were just trying to learn to classify an email like by sentiment or by topic. But now what if we wanted to not just encode an email, but then also generate one, like a smart reply. So as I said, this is a product that I learned a lot, so let's use that as an example.
It's really easy to get started. Cool. The other thing you should know is that TensorFlow is built on many different layers in its architecture. The hardware, the distributed execution engine, the Python front end. When you decode TensorFlow nowadays, you should use one of these high-level APIs, and that's exactly what this Getting Started experience is also teaching you. So that's really important, because there are many ways of configuring machine learning workloads. Sometimes advanced researchers, they need to go to this, down to this level, but that's definitely not a place where you should start. To build a model is really simple. This is an example in GitHub. You put a sequential model, you add a couple of layers, and then you can train and fit and evaluate this model. And then you can build these kind of cool classifiers that can take pixel inputs, and then through these weights and layers determine if it's a cat or a dog. So I said, training is one thing, then deployment is another thing, and to deploy on these mobile devices, we have a component of TensorFlow called TensorFlow Lite. Why is it called Lite? Because these mobile devices, they are not as big as the traditional desktops or whatever data center computers we might use for training, because that takes a lot of power. So TF